Hello, everybody. My name is Konstantinos Kytsios, and this is a video walkthrough of our ASE 2025 poster for our paper Detecting Semantic Clones of Unseen Functionality. Let me start with the task we're trying to tackle in our paper, which is the task of semantic clone detection. In this task, you are given two code snippets, and you want to build a classifier that predicts whether these two snippets implement the same functionality or not. And these two snippets are syntactically different in this case, because if they are syntactically similar, then there are other techniques to detect them. But if they're syntactically dissimilar, the state of the art is deep learning based techniques. In this task, we propose three main contributions in our paper. And each one is color coded with a different blue color here. And let me start with the first one, which is we propose evaluation methodologies that better align with real-world applications. But let me start from the beginning. Let me zoom in a little bit here. Okay, super. So let's have a look at how datasets for this task are in the literature. So a dataset, let's have a look at the first pie over here. And for now, let's ignore the blue and the yellow colors. A dataset consists of many functionalities. For example, the palindrome functionality, which checks whether a given string can be read the same from the beginning and from the end. The greatest common divisor functionality, the Fibonacci functionality, which returns the nth Fibonacci numbers. And for each functionality, the datasets contain many implementations, many clones of this functionality. So, for example, in data point here, it will consist of three elements. Two code snippets that and the label. For example, if the label is 1, means the two code snippets, both of them, they implement the palindrome functionality. Another question is, you have a data set like this. How do you split it in training and test set in a meaningful way? There are different ways to do it, right? The first one here on A, it splits also the functionalities. So in the training set, you have some clones of the palindrome functionality, and in the testing set, you have different clones, but of the same functionality, right? So we call it this one that you test on seen functionalities, because the clones you are testing on are unseen. So this portion is different than the yellow portion, but they are both portions of the palindrome functionality. There are different ways to split the training and test sets. For example, the one versus rest, you train on all the functionalities except one, and then you test on that one functionality. And this is here you test on unseen functionalities because you have not seen the palindrome functionality during training. And there is also a different way to test on unseen functionalities. If you do cross-data evaluation, where you train on all the functionalities of the one data set, and then you test on a totally different data set with totally different functionalities. Now, interestingly, what we found when we analyzed 9 state-of-the-art models in the literature, in the very recent literature, all of them evaluate the new model that they propose in A. So they evaluate the model on seen functionalities only. So they answer the question of how well can my state-of-the-art model detect clones of the palindrome functionality, given that it has seen different clones of this functionality during training. And we claim that this may not be aligned with what developers really seek in real-world applications, right? Because in real-world applications, you want your tool to detect clones. It doesn't matter. You don't want the tools to detect clones only of the handful functionalities you have seen during training. And we do a small-scale literature review to find specific applications where this would be useful, where generalizing outside the seen functionalities would be useful. And when we conclude that a clone detector should also detect clones of functionalities unseen during training in these applications. So our first takeaway is that for future clone detection, semantic clone detection models, we think that evaluating them also on unseen functionality can give a more complete image of the model's capabilities. And this motivates also our second contribution, which is, okay, state-of-the-art models, they're evaluated on scene functionalities. So we don't know how well they perform on unseen functionalities. So, okay, let us evaluate them. So our second contribution is an empirical evaluation of three recently proposed models that we see here on the left table, which is CodeBird, ASTNN, and CodeGrid. For now, we are only looking at the B subscript. For the CL, you have to wait until the third contribution. And we have here on the first column their reported performance on scene functionalities. You see it's very, very high, right? Near perfect. And then we evaluate them on the one versus rest split. We train on one dataset and test on another, and then the opposite. We train on the second dataset and test on the first. And these are two datasets only, but in our paper we also use a third dataset to have a more complete image, but here only on table fit. So let us say, for example, what we find is that the models they significantly perform significantly worse on scene functionalities, right? For example, let's have a look at CodeGrid here. On scene functionalities performed 97.8%. But in this cross-data evaluation, it even performed slightly worse than random guessing, right? This is a 48% drop in the F1 score. So this is pretty significant. On average, of course, it's slightly less, but still 31% drop on average for the models when they are tested on unseen functionalities. That's one part of our second contribution, but then someone may ask, what about LLMs? So these are models that are trained you split the data set, then you train them, blah, blah, blah. But someone may say, we have LLMs now that are very good in context learning. You give one example of a clone, and then they can answer whether a new example is a clone or not. And then we say, fair, let us also evaluate three state-of-the-art generative LLMs in an in-context setting. So for each one of those LLMs, again, we focus only in the B subscript. We give it an in-context example. And for the scene functionalities, the in-context example is from the same functionality as the example we asked the LLM to categorize. While on the unseen functionality scenario, it's different. So in the unseen functionality, we give the LLM an example of the Fibonacci clone and ask it to classify an example of a palindrome clone. And even here, we see a performance drop of up to 5%. Of course, it's much, much more robust than the trained models here on the left, sorry. But we still experience some drop here. For example, GPT-4o drops from 0.64 F1 to 0.59. So our takeaway for our second contribution is that models perform worse, significantly worse, when they are tested on the more realistic scenario of unseen functionality. And this now motivates also our third and last contribution to alleviate this drop. So we find a significant drop. Can we do better on the unseen functionality scenario? We take motivation from a technique called contrastive learning. Contrastive learning was introduced to deal with unseen events in computer vision. In this case, it was introduced to detect signatures of the same person using computer vision. To achieve this, the contrastive laws, so you train the model with your contrastive laws, it's equation number 1 here, and what you may want to see here is that you don't see the predicted label in the loss equation, right? So on contrast, in the second equation, which is the normal binary cross entropy loss function that you may use in a binary classifier, you see y hat I here. This is the prediction for the ith example. And you also see it here. So the binary cross entropy, or let's call it the normal training, where these models were initially trained, it optimizes it minimizes the classification error. And this may increase overfitting, right? Because when you reward the model, whenever it doesn't it predicts correctly, it will optimize for predicting correctly. This may lead to overfitting. In contrastive learning, on the other hand, you don't see the y hat term anywhere. So it doesn't optimize for the classification output. Instead, it directly optimizes for the similarity between clones. So let's take, for example, the case where yi is 1, which means that the two snippets are clones. So this term will live because this will be 0. So in this case, the loss function minimizes the distance between the representation of two clones directly without considering the classification error. And there are evidence here that this leads to better generalization to unseen events. So we tried this. We replaced the 3 classifiers of the 3 state-of-the-art models with a contrastive learning classifier. We retrained them from scratch, keeping everything else the same. And we show the results here on the table on the right with the CL subscript. And what we notice is we notice an increase on the unseen functionality scenario. A 9% average increase, right? It does not alleviate fully the drop, but it alleviates some of the drop. For example, it can go up to 26% in this case, where it went from 50% the accuracy to 67%. Then someone may ask again, what about generative LLMs where you don't have the capacity to train them most of the time? There, indeed, we try to mimic what the contrastive loss function does here, and by proposing a technique called contrastive in-context learning for LLMs. In contrastive in-context learning, we aim to steer the LLM towards the differences of a positive example and a negative example. This is the prompt that we use. We say determine whether C1 and C2 is a clone pair or not, and here are some examples. And let's say that our clone example is XY. In the baseline prompt, the non-clone example could be ZW, where ZW are of the same functionality or of a different functionality, depending on our scenario here, but they don't have any other relationship than that with X and Y. What we do in our contrastive in-context prompting is that we keep X the same. So X is the same as the clone example, and we find another W that satisfies the non-clone example. So it's like saying to the model, look, here X and Y are clones, X and W are not clones. So we hope to steer the attention of the model towards the difference of a positive and a negative example. We find that this also helps a bit with alleviating the drop. For example, in the llama case, we see a 5% statistically significant increase. For GPT-4o, we see a 3% statistically significant increase, while for DeepSeek, we don't find any statistically significant increase. But the takeaway of our third contribution is that contrastive learning improves the model's performance under the more realistic scenario of unseen functionalities. That's it then. Thank you very much for attending. On behalf of myself, Francesco Sovrano, Earl Barr, and Alberto Bacchelli, and looking forward to seeing you in Seoul.